Welcome to Mrs. Mahoney's podcast 3.4, our fourth in our Unit 3. We're starting on page 8 in the note packet, and today we're really going to focus on the electrons and how those electrons are arranged in the atom. The Bohr model so Niels Bohr put the electrons, realized he did some research, and we're going to talk about the emission spectrum next week and look at kind of how he determined this. But the Bohr model you've seen in middle school. It's when we looked at these electrons and that they are in orbits around the nucleus and in the first energy level. So each of these appears an energy level. So at the first energy level I can have 2 electrons. So right here and here, 2 electrons. That's full. You go to the next energy level. There I can have 8 electrons. Then I go out to my next energy level. There's 18 electrons. The Bohr model works. It only really explained the chemical properties of hydrogen. So they did more research, of course, and what we're going to be looking at is just taking where those electrons are. It's going to be similar, but we're just going to get a little bit more detailed of where the electrons actually are. So we're going to be using the modern theories called the quantum model. So this is, if you look, we're right on the page, top of page 8. The quantum model is pretty much what is being used today. And what they've done is say, okay, the electrons are existing in more of a 3-dimensional region known as an orbital, instead of just like on a train track that they can just be on a single track, you could almost say, or like an orbit that is really more 3-dimensional. Now, one thing with the quantum model, it's a mathematical model. This is probability. It's all looking at the probability of where that electron is at some point. But we do have similarities that it's going to be the same energy level as the Bohr's model. So if you look back and you're saying, oh my gosh, it's a mathematical model, that means there's going to be more math. No. We're not at the level that we can handle the math of the quantum model. I took it my senior year in college, and it was double, triple integrals, and it's just pure calculus. You definitely need to have a calculus base to really understand the math. So no, we're not going to be doing the math of it. We're looking more on the conceptual, and we'll let other people do the math. So the first thing is we need to say, okay, orbitals, right here. There's a difference between an orbital. So what we're going to look at is what did that orbitals. So we want to look at the orbitals. How do these orbitals even come up? Well, let's look at this. What this is, it's not a picture of thousands of electrons. It's one electron. Where is it the majority of the time? So if you had to call this a shape, what shape would you call it? Or where would you say that electron is most of the time? Hopefully you're all kind of seeing it's right there in the middle. It's a sphere. So they gave this the name of an S orbital, and they said that it's going to be a sphere shape. So in your packet, when I was talking about the shapes, you can draw a circle. 3-dimensionally, it's a sphere. Okay, at every energy level, I have this sphere. So this would be my first energy level. At the second energy, it's just a little bit bigger. Third energy level, again, it's just that area. This is the probability of where I'm going to find it. Okay, then they've given a name to another level. So at the second energy level, they've called these the P's. So if you look at, I have 3 P orbitals. There's a PX, a PY, PZ along the axis. To draw these, just do like a figure 8, a bow tie. I've seen them called snowman, 8s. Just so you have lobes up above and below. And that is my P. Okay, the D's. Don't try to draw these. And look at it when I'm going. And again, this isn't like some balloons exist in there. This is just the region where there's going to be the highest probability. But what do I need you to know about D's? I want you to know that there's 1, 2, 3, 4, 5 D orbitals. So don't worry about drawing the shape. The number of orbitals is more important. So I only have 1 S, 3 P's. There's 3 different P's, 5 D's, Hopefully you're seeing a pattern. And the last one that we will be looking at is the F's. And there are 7 F's. And again, it's not really looking like that. This is just saying this is where I have the likelihood that I'm going to find those electrons. So what else do I need you to know about those orbitals? So in each orbital, they can hold 2 electrons. So make sure I'd put right underneath there, I would know you need to write this down. So the s orbital, there's only one orbital, but can hold a maximum of 2 electrons. So 2 electrons in the one orbital. Those p had 3 orbitals. Each orbital can hold 2 electrons, so that's where we get a total of 6 electrons. My d, 5 orbitals. 5 orbitals holding 2 each, that's where it can hold 10 electrons. An f, 7 orbitals, therefore 14 electrons can go in each f orbital at one energy level. So advantages, why was this being used? The main thing is it explained the chemical property for all the atoms. The Bohr had some problems that worked great for hydrogen, kind of broke down when it was looking at some of the other atoms. That's why new research was done. Bohr, we talk about it in orbits. The quantum, you're talking orbitals. So just realize this is not a made-up number, or excuse me, made-up word. Orbitals is a 3-dimensional region. And then the big thing was the Bohr model really just didn't satisfactorily predict the chemical behavior and why certain atoms will react. So what do we need to do? We're going to have to give every single electron in an element a home. We're going to be telling so that if somebody's looking at this, it's like it's a zip code. It's the address for every single electron. But look at, here's our similarities. So just on the page 8, you have some space in there. I would write this down also. So at my first energy level, there's only a 1s orbital. So therefore, at my first energy level, there's only 2 electrons. Again, similar to the Bohr model. We're just being more specific. That second energy level, there's another s, but now I'm adding a p. So 2 plus 6, it can hold 8 electrons. At my third energy level, look at how it's building. I could have the 3s and 3p, that repeats. This is the first time I have a d orbital. So 2 plus 6 plus 10, that's my 18 electrons. My fourth energy level, there's my 4s, 4p, 4d. This is the first time we get that f orbital. Has a total of 32 electrons. Well, there's a couple rules, and one of the rules, only 2 electrons per orbital. Another rule, we're going to have to give them different spins. Another rule is that they have to go in certain energy levels. So we have different ways that we can start looking at the energy levels. Well, look at the bottom. And it's always lowest energy first. So first I'm going to put 2 electrons in this first 1s. Then I can put 2 electrons in the 2s. Then we said 6 electrons can fit in the 2p. Then I can have 2 electrons in my 3s. And then another 6 electrons here. But then it's like, whoa, wait, something gets a little weird here. Because really, in energies, my 4s comes before a 3D. So that's saying I'm going to fill in my 4s before I fill my 3Ds. Then I'm going to fill my 4Ps. Then there should be right here, there'd be a 5s and then a 4D. So this is where things get a little weird. So we need to find a tool to be able to help us to know how to fill these. This is something the books use, other people, different teachers have used. You can probably see it on the web, on different websites. If you Google electron configuration, order of filling, or something like that. And what this would do, you're following the arrows. So you fill the 1s first, so it'd be 1s, 2 electrons in here. 2 electrons in my 2s, and I'd be following the arrows. Okay? Problem is, I wouldn't give you this on a test, and you would have to redraw it, and I actually think it's kind of confusing. So I want to look at something that we already get to use on every single test that I think is easier to fill. So look at the top of page 9. You have this periodic table. I would color code it very similar to this. I mean, obviously you don't have to use exactly the same, but we're separating it. This is the periodic table. So if I look at here, so if I look at this, I have right here 2 columns, my first 2 columns. So this is known as the S block. And we said that each S can hold 2 electrons, 1, 2. Over here, when I'm counting here, 1, 2, 3, 4, 5, 6. This then is a P block. Each P, we said, holds 6 electrons. There's 6 columns. Look in the middle. There are 10 columns. So therefore, the middle section, this is a D block. And if you count bottom on down here, there's 14s. This is the F block. So when I'm numbering up here, you can pretty much, as you go down, this would be 1s, 2s, 3s, 4s, 5s, 6s, 7s. Then over here, my P's, notice we don't have a 1p because we didn't start having P's until we got to the second energy level. So this is a 2p, 3p's, 4p, 5p, 6p, 7p. So the S's and the P's are the same. Where you have to be aware and say, here's where something's a little weird. This is a 3D. So it's a 3D even though it's in the 4th period. But this is the first time we have a D block. So these are 3Ds. This would be 4D, 5D, 6D. Where's the first place we have F's? Down here at 4. So this would be the 4F and a 5F. So down this, these would be 3P's, 4P's, 5P, 6P, 7P. Same thing. Looking at that. Well, we're going to just read it like an old-fashioned typewriter. We're going to just start filling electrons in as you read it left to right. So if I go all the way across, when it's full, I've got 2 electrons in the s orbital on the first energy level. Let's look at another way. So this is the same thing, color coding. Look at the arrows. We're just going to read it left to right, going across, and filling the electrons as we go across. So you need your periodic table in front of you, and we're going to just start putting some electrons in. Okay, so we're going to just start putting some electrons in. Now here are the 3 rules I kind of talked about. The Aufbau saying we fill from the lowest energy to the highest energy. Following the periodic table will take care of that. Hund's rule. Okay, this is saying that you're going to each, so what we're going to do is give an electron is going to be like an arrow. We're going to represent 1 electron as 1 arrow. So they want their own space before they start doubling back up. And then we have a maximum, we said only 2 electrons per orbital, so you can only, the maximum, have 2 electrons per line. And then to, again, because of numbers, and we are going to look at a little bit at quantum numbers, we just can't have them being the same. So we're going to have, when they have to share a line, one's going to have to go up, one's going to have to go down. It doesn't matter if you start with all ups or all downs. I just have to have 1 up, 1 down. Okay, so what happens if I was filling this in then? I would just start saying, okay, let's look at hydrogen. Hydrogen has 1 electron. I know that's because it's atomic number 1. So how would I show that? Just 1 electron in the 1s. So this is 1 electron in the 1s orbital. Helium has 2. So what would I do? I would put it as 2 electrons. Then that's full. I cannot put any more on there. So if I went down to lithium, then notice we go into a new energy level. So I would be at the 2s. That's 3 electrons. That would be lithium. This would be 2 electrons in the 2s orbital and 2 electrons in the 1s orbital. Now at the p, if I keep going across, what would be next? Boron, it has 5 electrons. Carbon would have 6 electrons. Nitrogen, 7 electrons. Then I could go through and I'd start doubling back up. Oxygen would have 8. Then I'd have fluorine, and then I would have neon. So when I'm looking at this, writing for oxygen, and I'm looking at it on my periodic table and going, okay, oxygen, I know I have some in the 1s, there's some in the 2s, and I'm ending up at that 2p, looking back at my periodic table. So to write for oxygen, I don't have to write all the orbitals I don't use, but I would just say 1, 2, 3, 1. And this is showing you that it needs 1, 2 more to be full. That's why oxygen forms at -2. Okay, sulfur. I'm going to kind of skip chromium for a second. But look at right here. No, I'm not. I'm coming back up. Look at what happens right here. If I go across 1s, I'd have 2 electrons. And it's full. So then I have to go to my 2s. It has 2 electrons. Okay, now my 2p, when I go all the way across and I know it's full, I just go ahead and fill it up. I know that they filled one, then doubled up, but since it's full, I don't have to show that. Same thing, 3p, it's full. So I'm going to just show that it's a full orbital. 4s. Okay, now is when I came to that 3d. Same thing, as I'm filling it up. 1, 2, 3, 4. And actually chromium's an exception. We'll kind of come back and talk about what chromium really does. But for right now, that'll be okay. Okay, do I always have to write arrows? We're going to save this because I want to do these tomorrow in class. But let's go down. Do I always have to write these arrows? Because really they're getting a little annoying. No, we don't, thankfully. What I'm going to do is, look at, I have this right here. This is called the complete configuration. And so instead of doing arrows, I'm going to write, for every arrow, it would just become a superscript. So hydrogen, we said we had 1 electron. So I would just write that as 1s1. Let's look at what this means. This superscript is number of electrons. The s is telling me what orbital, and the big number in front is telling me energy levels. So we're just giving every electron a home. So this is saying there's 1 electron in the s orbital on the first energy level. Helium has 2 electrons. Now you don't have to always start at the beginning and say 2s1, 1s1, 1s2. If it's full, you just write it as full. So this has 2 electrons in the s orbital on the first energy level. I just read right to here, it's full. Okay, lithium is right here. So you always have to start at the beginning. Well, there's 2 electrons in that 1s orbital. Now it's full. Then I know I'm going to have 1 electron in the s orbital at the second energy level. Beryllium, 1s2, 2s2. 2 electrons in the s orbital in the second energy level and 2 electrons in the s orbital in the first energy level. Neon, okay, neon's all the way over here. So again, we always have to start in the beginning. 1s2, it's full. 2s2, it's full. What do I come to next? It's a 2p. How many's in there? 1, 2, 3, 4, 5, 6. When I go all the way over, it's a 2p6. Now there's a double check. How many electrons does neon have? It has 10. Add up your superscripts. 6 plus 2 plus 2 is 10. So you have to take care of all 10 electrons. Magnesium, element number, it's right here. So again, I'm going to start at the beginning. 1s2, went all the way across it. 2s2, it's full. 2p6, it's full. Then I would say 3s2. Okay, now you don't always go all the way across. I'm going to add another one. Let's look at oxygen. Up there we had written the arrows for oxygen. Oxygen, I would stop right here. So I start at the beginning. 1s2, 2s2, 2p, but we have to count. How many p's are there? 1, 2, 3, 4. There's only 4 electrons in the p orbital, the second energy level, 2 in this s at the second, and 2 in the s at the first. 4 plus 2 is 6, plus 2 is 8. All 8 electrons have found their home. Okay, iron, last one I'm going to do. Start at the beginning. 1s2, it's full. 2s2, it's full. 2p6, 3s2, then we're coming over here, going all the way across. So I say 3p6. This is where we're at. We're going to start right here. 4s2. Then this is where, oops, okay, we come to a 3d. Remember, 3d, not 4d. And then you have to count how many over is iron. And it's 1, 2, 3, 4, 5, 6, 3d6. If you add them all up, it adds up to the 26 electrons. Plus, if we look, we can start realizing anything in that column is going to end in a d6. Anything in this column is going to end in a p4, p5s, p6s. You start to see the habit, you start to see the pattern as we're going through it. Okay, this is going to be a fun one. I want you to try gold. Then tomorrow, this is just what we're going to be working on for the next couple days. We're just going to be practicing in this. I know you're going to come with questions, but give it a try and come with questions, and then this is just what we're going to be practicing tomorrow in class.